In lesson 1.6, we'll be going over some two-dimensional figures. We're going to be learning a lot more terms here. Remember, we're building our structure of geometry. We started with just our three undefined terms. We've been doing a lot of definitions. We've had a few postulates and a few theorems, but right now we are kind of sticking in this spot right here, talking about a lot of definitions. We want to know these definitions and have a good working understanding of those. So this lesson starts talking off just mentioning tessellations. They mention them because it's two-dimensional shapes. And there's some pretty cool things that you can do with tessellations. A tessellation covers a plane with a pattern of one or more geometric shapes so that there's no overlaps or gaps. So like a simple one is you can have just a bunch of the same size. Now, I just did not get those the same size, but if you had the same size rectangles, and you can use that to cover an entire plane. Again, these are supposed to be the same size. I'm not doing real great here, but then there's actually a lot of cool things you can do with those. So you could look into tessellations if you wanted to. Definitions involving curves. So this, we're going to use these definitions here, and they actually help us define things later. So these aren't like main terms that we learn, that we study a bunch of properties of curves or closed curves or simple closed curves, but we have these definitions to help us define things later. So a curve is just a continuous set of points. So there's an example of a curve. Just there's no gaps in it. There's just a continuous set of points. Would this be a curve? Actually, in our geometry definition, that should be a curve, even though I tried to draw it straight. It's still a curve because it's a continuous set of points. Even this, in our geometry definition, would be considered a curve because it's a continuous set of points. So we have to make sure we understand things in their geometry definition when we're talking about geometry. A closed curve is a curve, all right, so it's still a curve. That begins and ends at the same point. So here's a closed curve. Here's a closed curve. So as long as they begin and end at the same point, that one wasn't great because I accidentally overlapped, but as long as they begin and end at the same point, it's a closed curve. So that's a closed curve. Gotta be careful here because I don't want you to think that's a simple closed curve. Now, if we like did a bow tie looking thing, that's a closed curve. Now a simple closed curve is a simple curve is a curve that does not intersect itself. So that's a simple curve. This is a simple curve, unless the starting and ending points coincide. So we could have a simple curve that looks like this. And that simple curve happens to also be a simple closed curve. So a simple closed curve, our last one, is a simple curve that is also a closed curve. So we actually sketched a few of these already. All these highlighted ones here, these are simple closed curves. Note the set of points do not have to be coplanar. So right now we're drawing them all on the same plane. They don't have to be coplanar. You could try to think of maybe a necklace hanging off a table. So here's a table, my amazing artwork here, and there's a necklace that's hanging off the table. Part of it's in the plane of the table, and then part of it is hanging off and in a different plane. Not a very good drawing. All right, classify. The example here, classify a triangle as a curve. Is a triangle, does it fit our definition of curve? Not our normal understanding of curve before today, but our definition of curve from today, continuous set of points. Well, yes, it does. It's a continuous set of points. Okay, is it a closed curve? Closed curve, a curve that begins and ends at the same point. Yes, yes, it does. Is it a simple curve? Curve that does not intersect itself unless at the start and end point. Yes. Therefore, a triangle is a simple closed curve. All right, so some definitions involving curve. Probably very new to us, but important as we build our structure of geometry. All right, circle definitions. If I'm in class teaching this, I often like to ask you guys for the definition of circle. Rarely do people come up with it. We know what circles look like, but sometimes they're hard to define. So a circle is the set of all points that are a given distance from a given point in a given plane. So this part down here, I'm actually going to start with this. This means all these points are coplanar. And they're a given distance from a given point. So I'm actually going to work backwards here. So let's say this is our given point, and we want a given distance. Well, we want the same distance all the way around this point. Do my best here. My best is not going to be great, but this is supposed to look like every distance here is equal. And so this part right here would be our circle. It's the set of all points that are a given distance from a given point. We name a circle by its center. So if this was a Q here, we would call this circle Q. Circle Q. Circle Q. And the circle does not include Q. That's not part of the circle. The circle's the points out along here. The interior of a circle, the set of all planar points whose distance from the center is less than the length of the radius. It seems like we should have defined radius in here. So radius is the given distance. That's the radius. So the interior of the circle is all points that are at a distance less than the radius. Well, that would be everything, all the points in here. That's the interior, which makes sense, like inside, interior. And then the exterior, the set of all planar points whose distance from the center is greater than the length of the radius. So that would be everything else, which is all this stuff way out here, like the whole page. So there's that. And then the Jordan curve theorem, which we'll talk about interior and exterior, says a simple closed curve, which I have to the right here, this funny looking smushed Pac-Man, divides the plane into three disjoint or separate, like no points are in common, sets. The curve itself, so in our case, this light blue funny shape, just that curve, just those points, that's one of the sets. The interior, that's all this stuff in here, the interior. Oops, I did not mean to color over the blue. So all the interior, that's the second part. And then the exterior, everything else. So that is the Jordan curve theorem. Every simple closed curve divides a plane into three disjoint sets. Now, a region is the union. So we learned that term union before. So we would include everything that it talks about is the simple closed curve and its interior. So when we talk about a region, we're talking about, I'm tracing it over it, this simple closed curve and its interior. So, and everything inside. So that is known as a region. So lots of terms here. And we actually had a theorem in there. Convex and concave, we'll define these There's sometimes an easier way to think of these, but a convex set has the property that any 2 points of its 2 points determine a segment contained in the set. So these are talking about two-dimensional shapes. So is this convex? Well, if we choose any two, not just two, any 2 points, if we connect those 2 points, is that segment still within the region? It is. And if I choose any 2 points, doesn't matter what two, it will always be in that region. So that's the definition of convex. Concave is a set that is not convex. And so an example of that would be something like this. We can choose some points that if we connect them, that segment lies in there, but we also, like if I chose this point and this point, if I draw that segment, it goes on the exterior of my shape. So therefore it is concave. Now, a quicker or easier way to remember these, concave shapes cave in somewhere. The other word cave is in there. So that's concave, and convex don't cave in. All right, it's page 1. We're through page 1 of those notes. Let's go to the next one. Talking about polygons. A polygon is a simple closed curve that consists only of segments. Only of segments. So it's got to be simple and closed and contain only segments. So I attempted one there. Triangle. It's a polygon. So those are some examples of polygons. And let's put a purple one. This is not an example. So this one's made only of segments. It's a closed curve, but it's not simple. So the purple ones again are not. What about this? Maybe the capital letter D. Oh, that's a nice shape. It has a simple closed curve, but it's not only made of segments. So these purple ones are not polygons. The other ones are. The side of a polygon is just one of the segments. So if you take a shape in this one, here's a side, there's another side, there's another side, and another, and another, and another. So those are called the sides of a polygon. Vertices, or vertex is singular, vertices is plural, is an endpoint of a side. So here's a vertex. Here's a vertex, 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 and vertex. Plural is vertices. And then angle. An angle with two properties. Its vertex, so remember angles have a vertex, is a vertex of the polygon, and each side of the angle contains a side of the polygon. Let's go to orange. So here is an angle in a polygon. This one right there. All right, so that's an angle of a polygon. Example, determine which or whether each figure is a polygon. Looking at this first one, is it a simple closed curve? Yes. Is it made only of segments? Yes, so it's a yes. Second one, is it a simple closed curve? Yes. Is it made only of segments? Nope. So this is not a polygon. Third one, is it a simple closed curve? Yes. Is it made only of segments? Yes. So this is a yes. Last one, is it a simple closed curve? No. So even though it's made only of segments, it's not a polygon. And then lots of our special names of polygons. Triangle, 3 sides. So we can have triangles. We'll be discussing lots of triangles. Quadrilateral has 4 sides. We'll be discussing lots of quadrilaterals. Pentagon, 5 sides. 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5. It doesn't have to be convex. Hexagon has 6 sides. Typical hexagon we see might look like this. Heptagon, 7. So you can keep doing these. Octagon, 8. Nonagon, 9. Decagon, 10. And dodecagon is 12. And then if we use anything besides that, we say an n-gon. So maybe like a 15-gon or a 17-gon. Guess how many sides a 15-gon would have? It would have 15 sides. Okay, some special polygons. An equilateral. Lateral means side. Equilateral means a polygon in which all sides have the same length. You notice in that one, they're all marked with the 2 tick marks. So that is an equilateral polygon. Next one is equiangular. So a polygon in which all angles have the same degree measure. Notice all in this, what is this, a hexagon? All the angles are marked with this simple gray arc, so that all those angles are equal. So that's a equiangular. And then regular. We often miss this. Regular does not just mean plain. Regular has a very specific meaning. It is a polygon that's both equilateral and equiangular. These are the ones that usually are on, like when little kids are learning shapes, they would have regular polygons on those. So a stop sign is a regular octagon. A square is a regular quadrilateral. And then a diagonal, any segment that connects 2 vertices but is not a side of a polygon. So if I pick this vertex and this vertex, that is a diagonal. If I pick this vertex and this vertex, this one's a diagonal. However, if I choose this vertex and this vertex, that's not a diagonal because it's a side, and it's not allowed to be a side. All right, stay with me a little bit more. Polygons are named by listing the vertices in consecutive order, clockwise or counterclockwise. So let's name each vertex here. We could name this polygon A, B, C, D, E, F, G. We could name it, let's start with D and go this way. We could name it D, C, B, A, G, F, E. There's all kinds of names for it, but as long as we list them consecutively, we can go clockwise or counterclockwise, and we can start with any letter we want. The interior is in here. If you take all the interiors of the angles, you have the interior, and the exterior, of course, would be all out here. Example 3, classify each polygon by its number of sides, then state whether it's concave or convex, and determine if it's equilateral, equiangular, regular, or none of these. Okay, looking at this first one. Let's count the sides. I'm going to mark one so I know where we started. So that's 1, 2, 3, 4, 5, 6, 7, 8. That's 8 sides. That's an octagon. Octagon. It is convex because it doesn't cave in at all. And it is regular because it's both equilateral and equiangular. Our next one, let's count those sides. 1, 2, 3, 4. So it's a quadrilateral. Next, we want to name it it's concave or convex. Well, it's convex. It doesn't cave in at all. And it's neither It's not equilateral or equiangular because we have different size angles and different size sides. This one that looks kind of like a cat is, let's count the sides. Let's start with this one. 1, 2, 3, 4, 5, 6, 7. So that's a heptagon. And all the sides are marked equal, it looks like. So actually, we're not there yet. It is concave. Uh-oh. And lastly, it is equilateral. It's not equiangular, just equilateral. Perimeter, the distance around a closed curve is called its perimeter. To find the perimeter of a polygon, add the sides. If it's a regular polygon, you just take the length of one side and multiply it by the number of sides. So number of sides times the length of one side. Nice and simple. And then we have circles. We already mentioned the definition. Actually, I kind of must have put this in the wrong order. We got circle, the set of all points in a given at our given distance from a given point in a given plane. We name a circle by its center. So we could call this, let's call it circle C. Radius is a segment that connects a point on the circle with its center. So a circle can have a lot of radii. There's one of them. It's a segment. So let's say this is R. So we would say this segment is RT. We name it as a segment. We don't have to say radius RT. We just say segment RT. Oh, I'm sorry, not T, it's C. Is a radius. A chord just connects 2 points on a circle. So there's a chord. It's also a segment. So we just say segment JK. Diameter is a special type of chord. It's a chord that passes through the center. Let's get a different color here. Let's go orange. A chord that passes through the center. So JM here, segment JM is an example of a diameter. And an arc, it's a curve that is a subset of a circle. So here's the circle. We want a subset of it. It's a curve, so it's continuous, so we could stop there, and we would call that one RJ. And you put a little arc over it like that. Realize that a diameter is 2 times the radius. So if we look at our orange diameter here, there's a radius and another radius. So diameter is 2 times the radius. The distance around the circle is called the circumference. And a lot of us had heard this term pi before. We know it has to do with circles, but not everyone knows what the definition of pi is. The definition of pi is the ratio, so a fraction, of circumference over diameter. So we use the symbol pi is equal to circumference over diameter. And in any circle, the circumference divided by the diameter is 3.14159, dot, dot, dot. It goes on forever and ever. To find the circumference, if you know the diameter, it's just pi times diameter. If you know the radius, it's 2 times pi times the radius. Find the missing measure. Well, we want to find R here. If the circumference is 10, I know that's hard to see, but we know the circumference is 2 times pi times R from this line up here. Well, we know the the circumference is 10 centimeters, equals 2 pi times r. Well, this is about 3.14. Use a calculator, or just in your head you can multiply this out. This is 6.28. And divide both sides by 6.28. I don't have a calculator with me, so I'm going to let you guys do that. The radius is going to be 1 point something centimeters. So figure that out. And then the next one says find the circumference of a water tower that measures 60 feet across. Well, 60 feet across would be diameter. So we know circumference is equal to 2 times pi times r. Well, it didn't tell us radius, it gave us diameter. So what's the radius? It's 30. 2 times 3.14 times 30 feet. That's 6.28 feet. I'm sorry, 6.28 times 30 feet. And once again, I will let you multiply that out and find the actual circumference. Lots of information, lots of definitions. So we need to get a working understanding of these definitions.